good to do them early in the course when things aren't that busy. Assignment 1's been released, so it's on Quarkus. It's due October 9th. You're writing in HDL a simple computation circuit. So it's basically an approximation to the exponential using a Taylor series expansion. So it's pretty common that when we write hardware, we want efficiency. So we don't complicated function like an exponential, which comes up a bunch in deep learning, for example, we might approximate. So the example that you're optimizing is such an approximator, where you find a simpler representation that's close enough. A bunch of this assignment is actually kind of a tutorial to make sure you understand how to use FPGA CAD tools, how to use simulators. So you learn how to use Quartus, you learn how to use model sim to simulate for correctness. If you already know how to do those things, then you got to step ahead, but we don't assume you know how to do that. And you probably haven't used all the features that are available in Quartus or model sim, even if you've used them before in your education. If you've been using them in your job, maybe you do know all the features. So the assignment document looks pretty long, but don't be intimidated. Most of that is kind of tutorial of, okay, let's walk through and try this and so on to guide you through how to use the tools well. So we basically have given you a simple implementation of this design that works, but it's not very high performance. So you're going to take that, you're going to run all the tools so that you can analyze it, see how it works, verify that it's correct, and then you're going to make 2 other versions of it, building off of that code that are, use different computation styles that we talk about here, and are hopefully higher performance. Let's see, this is kind of the details of how do you start the tools, but it's all in the handout. The easiest way to do this assignment is just to use the UG machines. How many people know what I'm talking about when I say UG machines? Have used them before? How many people are going, what is a UG machine? Okay, so a few. So UG machines are the machines that are available basically to all students, undergraduate and graduate. In this assignment handout, it lists there's 4 different lab rooms where you can go to. The door code is 2 to the 16th. So it's easy to remember for engineers or computer engineers, hard to remember for other people. So you can get there anytime you want. There are lots of workstations. And these tools, Quartus and Model Sim, are pre-installed. Use these commands to start them. You don't have to remember that. It's in the handout. You can also access those machines remotely. So on the course website, I've included a guide to VNC and remote access. VNC is a graphical remote viewer. Okay, it lets you log into a machine that's somewhere else and just see exactly what's on its desktop. So I posted the guide from an undergrad course I teach about exactly how to do that. So you can use these UG machines from anywhere. So you can use them from home. So that's kind of the easy way to do this. You don't have to worry about any licensing issues. You don't have to worry about any setup. The somewhat harder way to do it is you can install Quartus and Model Sim on your own machine. It's not that hard. There's also an appendix in the assignment that says how do you do that and point those tools at the license server here at U of T. So if you really want to have it on your own machine, you can do that. You're just going to go to the back of the assignment document and follow the instructions. Does it all sound good? Most people choose to do this because it avoids all licensing issues. It avoids me having to debug licensing issues. Everybody's happy, right? But if you really want it on your own machine, it's definitely doable too. Okay, so actually it looks like there are a bunch of comments in the chat. Let me just see if this is all people saying. All right, good. Okay, so good feedback in the chat. Amin has done well. I guess people here in the audience are the ones who really appreciate Amin are the ones who can't actually express feedback to him, but you can type it in the chat. So thank you, Amin. Okay, so I'll show you the survey results. Most people here know Verilog, but not everybody. So if you know VHDL, you won't find Verilog very hard to learn. They're not that different. Because the test bench that we give you in this assignment and the next one are written in System Verilog, it's probably a bit easier if you do this in Verilog. So if you know VHDL but not System Verilog, you might use this as a motivation to go learn System Verilog, and it won't take you that long. If you really want to write it in VHDL, it's fine. You can do that. You just have to basically make sure that the test bench is correctly connecting to your hardware. If there are a few people who don't know any HDL, so you will need to pick one up. And good resources on this. What we use for our own undergrads at U of T is this book by Brown and Vraniczek, a professor and a professor emeritus at U of T. We're not the only ones who use this. It's a best-selling Verilog textbook. So there's a couple copies in the library, and you can go buy your own if you want to learn how to do basic digital design in Verilog. System Verilog is really just the next version of Verilog. Okay, I don't know exactly why they gave it a new name, but they did. It's really just the more modern version of Verilog. If you want to, if you are going, I'm not quite sure how to use System Verilog, but I know Verilog, I want to know what's new about it, you can go to this link. If I'm not quite sure how to describe digital hardware in HDL or I'm rusty with it, this link is good too. So it's a tutorial. It's 4 sets of lecture slides from another university. And actually the professor who posted these slides, the server's gone down, so this is a link to the Wayback Machine. I like these slides, so I went and found an archive of them. So if you click on this, you can go look at those slides. It's a very, I think, readable tutorial of, okay, I just want to describe digital hardware. Exactly how do I do that in System Verilog? I don't really want any philosophical discussions. Just show me exactly how to do it. So yeah, it's a good resource as well. If you know HDL pretty well and you're like, I want to know some best practices, this is a much more advanced resource. You don't have to read it all, but if you're curious, this book is by a well-known hardware description language trainer named Sutherland, and it basically focuses on how do we use System Verilog to do design. So you can use System Verilog either to simulate your design, so basically write very fancy test benches, or to describe your design, what's called synthesizable designs. We care about the synthesizable part. We're trying to make hardware. We already wrote the test bench for you. You don't have to worry about that part. And then if you also, another advanced reference, if you're curious, Cliff Cummings is another well-known Verilog trainer. And these are papers that he has written on good coding style in Verilog, like gotchas, things to do, not do. Again, you don't have to read them for this course. We're not going to be writing things that advanced, but if you want to improve your skills, you might go look at them. Yeah? Oh, so things are not going well? Sorry. It did seem too easy. Okay, make you co-host. How's that? Let's see what we're sharing here. Let me just. Okay, if you read the guide of how you'll be marked on this assignment, about half of your mark comes from just optimizing the hardware well and making it work. Another 40% I think we put is for the quality of the report and answering all the questions we asked, and about 10% is from coding style. So we're actually going to look at how you wrote your Verilog, and we want it to be well-structured, reasonably readable. So a few tips. Well, how many people here know Verilog versus System Verilog? So how many people know Verilog but have never used System Verilog? Okay, a few. How many use VHDL but I've never used, okay, but haven't used Verilog? Okay, and how many people know System Verilog? Okay, so the class is reasonably evenly split. And then how many people, you don't have to say, I guess you can keep silent if you're worried, but basically if you don't know any HDL, anybody in that category? Okay, so a few. So if you don't know any HDL, I'd recommend that textbook by Brown and Vraniczek. If you know Verilog, well, you basically know System Verilog, because System Verilog is just the next generation standard, but it cleaned up some nasty things in Verilog. So first thing is, in Verilog, the fundamental unit of computation is kind of the always block, like when something changes, do this. And System Verilog basically makes two versions of this. They make an always comb and an always FF. Verilog was originally written as a simulation language. It wasn't really made to describe, here's some hardware that I actually want you to create, which is called synthesis. People essentially adopted coding conventions that CAD tools could interpret as that's a flip-flop, that's an AND gate, that's a mux, etc. And if they didn't quite follow those coding conventions exactly, they sometimes could get unexpected hardware. System Verilog basically makes two versions of this always block, one of which says I'm making a flip-flop, and the other says I'm making combinational logic. And that kind of cleans up your code, makes your intent more clear, and if you get it wrong, you actually write something that isn't a flip-flop in an always FF block. It says this doesn't really make sense. There's also, in Verilog, one of the most bizarre things is you have to declare variables of two types, wire and reg. If you ever had to memorize these rules, you can now just forget them, okay? Because the rules, they convey no information. It's just this thing must be declared wire, this thing must be declared reg. System Verilog basically defines a new type called logic, and you can just call everything logic, okay? So just forget about, if you studied this and you got a good mark on your undergrad course exam for understanding wire and reg, well done, right? So you earned that mark, and now you can just forget it and just use logic because it's way easier to read. General good code, this is true of hardware description languages, all software languages. Comment your code. Don't have magic numbers, so use enumerated enums or parameters so that you name states. The third part of this assignment, you're going to need a little state machine. So it's better to give the states names, not to have a bunch of like test if the state equals 1, 1. Try to avoid duplicated code. So you can do that by making a module and instantiating it repeatedly, or you can use, there are two kinds of looping constructs, generate and for loops, that you can use to create repeated code. You don't have to do anything super fancy, but basically if you find I'm typing the same thing, I'm cutting and pasting the same thing over and over again and changing two signal names, take a look at that and see if that's the best way to do it. Make your names meaningful, okay? So if your names are I, J, K, in, out, interior 1, A, B, that's probably bad, okay? So give them good names. Okay, so that's just kind of some tips on how to get going on the assignment. If questions come up, ask on Piazza, and Amin or I will answer. And I do keep track of like good questions on Piazza and kind of use them as a kind of bonus set of, give people some bonus marks at the end of the course if they've been very helpful to their classmates or come up with some good questions, found things that didn't work. Okay, in this assignment, you're using fixed point numbers. How many people know what fixed point numbers are? Okay, so quite a few. How many people have never heard of a fixed point number? You're not quite sure what this is. Okay, so at least a few. So fixed point numbers are just integers. Okay, so let's take a 16-bit signed integer. The range of values that it can represent is from negative 65,000 and something to positive 65,000 and something. And we have the lowest order bit represent ones. The highest order bit represents 2 to the 15th. So the precision of this is 1 unit. So meaning that we can represent, the error in representing something is at most 1 unit, right? We can represent every single integer without any round off. And our range is what I just said. Okay, we can reinterpret an integer. So we can write our HDL where we declare it as, it is an integer. We work with it as an integer, right? So it's just a vector of bits. We can reinterpret that as fixed point. Doesn't change any of our hardware. We're just remembering where do we think the decimal point is, and that's called fixed point. So for example, in this assignment, your input is in fixed point, 16-bit precision still. So, but we're interpreting it as there are 2 bits to the left of the decimal point and 14 bits after. So 2 integer bits, 14 fractional bits. That means our range is from about -2 to +2. Okay, so to be precise, it's maybe slightly less than that, but I'm not going to go through the whole calculation of exactly how close we get to 2 and -2. And our precision is 2 to the -14, because that's what the value of our lowest order bit is. So we can represent numbers that are 2 to the -14th apart, and we don't overflow until we get to +2 or -2. So all we're doing basically is still using a 16-bit integer, and we use add, subtract, multiply, everything on that 16-bit integer, and we just remember that we're interpreting it as having a decimal point after the second bit. Does that make sense? You don't have to do anything else really in your Verilog. Okay, so I already said this. Basically, you can do all, yeah. Isn't the Q for Yeah, Q 2.14. You're asking, what does it mean? Yeah. Well, basically it's 2's complement, right? So the reason this only goes to +2 is basically if I put, let's see, a 0 here and a 1 there and 1's all along here, I get something that's just a tiny fraction less than 2, which is basically like that. I got a tiny fraction less than 2 to the 16th. On the negative side, I'd put a 1, like all ones. If I complement that, I basically am actually going to get all the way to -2. Does that make sense? So yeah, so sign bits it's still 2's complement. It's just like the same integer representation we usually use. Yeah.
I got another question for the integer bits. So there are only two bits for the integer bits, right? So
Yeah, in this choice that I've made, I've said we're going to interpret our input as 2 input integer bits and 14 fractions.
yeah, and for the range, there is a -2 to +2. It should be file numbers between the
It should be,
file numbers, file integers, like -2, -1, 0, 1, 2.
well, range is just what is the range of numbers you can represent before you overflow. Okay, so it can go from -2 up to 2, but actually very slightly less than 2, right? That's why I put the tilde in. And then the precision is how small an increment can I do such that it's not just thrown away. Okay, so the precision is 2 to the -14. But this is just, it's a scaling basically. It doesn't actually change what hardware we build. So you write your HDL where you just add, subtract, multiply as if they were integers. So you get a very efficient hardware by doing this, but when you're writing your HDL, you have to keep track of where that implicit decimal point is. Okay? So for example, if I take 2 of these fixed point numbers, so 2 integer bits, 14 fractional bits, I add them, well, I could get up to 3 integer bits right now, right? Just like I add 2 16-bit numbers, I could get a 17-bit output. So this is the same as integer. My decimal point didn't move. I just remember, okay, this is how I should interpret those 17 bits. It's now 3 integer bits and 14 fraction rather than before it was 2. Okay, and if I want to make sure I don't overflow, I should have a 17-bit output. If I multiply 2 of these numbers, I actually get 2 16-bit numbers, I get a 32-bit output. And if you just on pen and paper work out where is my decimal point, you get 4 integer bits, 28 fraction. So you just have to remember where is the decimal point sometimes. The truth is you can write a lot of your Verilog and you're like, I don't care. Decimal point's just, it is where it is. But sometimes you have to think about where is my decimal point because I want to extract the most important bits or I might want to round off. So now I need to know where it is. So if I do a lot of adds and multiplies, I might wind up with, if I just say, well, I'm going to keep all the fractional bits and I'm going to make sure there's never a possibility of overflow, I might wind up with integers that are actually getting pretty big. And that makes my hardware too big. So we tell you in the reference solution we've given you, okay, here's where you can round off. Okay, so you can just extract some of these bits. The output for this assignment is 7 integer bits, 25 fractional bits. So your intermediate results, if you want, you can make more accurate than that. But you have to keep track of where your decimal point is just so that you extract the right bits at the end. Does that make sense? One last question. Why do we ever use fixed point instead of floating point? So floating point, I guess you've used floating point obviously in software a lot. Floating point fundamentally stores things a little bit differently. It has a mantissa, which is basically an integer, and it has an exponent, right? It's scientific notation. So we could do that as well. There are 16-bit floating point formats that would divide these bits into basically an integer part and then an exponent part. Why? And we could do that, but we didn't do that in this lab. And it's pretty common in signal processing not to do that. Why? What do you think?
Floating point numbers, multiplication, addition, and all those operations are very expensive. They take up a lot of area.
Yeah, so basically we could do it. It's convenient, but it does cost more hardware, right? We wind up with a lot of shifting numbers around to align before we can add 2 floating point numbers, if they have 2 different exponents, we actually have to do shifts to make their exponents the same. Then we can add them. Then we have to check, should we do another shift to kind of put them back in their normal range and change the exponents some more? shifters are actually pretty expensive. So all this is actually extra hardware. If you have very little idea of your dynamic range, you might have to do it. In this assignment, we know our dynamic range pretty well. We don't have to do it. So it's more efficient in hardware if you can use fixed point to do it, although you can't always. Okay, so that's it for assignment 1. Any questions on that? Okay, so in that case, I'm going to keep going. Okay, so this is like a concept map of how do these things fit together. One of my own grad students, after he took this course a few years ago, said, "You talk about lots of concepts, and I didn't really understand how they fit together, right?" So I thought, oh, okay, I should probably like show you a chart. So this is my attempt to address his feedback on the course. So what are we talking about this lecture and next? How do we organize hardware with compute models? And that's a useful concept, particularly for FPGAs, because they can do so many different things. So what are some ways of thinking about computation? All right, and with that, I'm going to switch to the chalkboard for a while. Assuming I can make this go. Yeah. Okay, so the reconfigurable computing textbook tries to make a distinction between compute models and system architectures. Compute models, how you're thinking about organizing your computation, systems arcs, what you put in hardware. In my opinion, there's not a fantastic line between them, so I'm just going to kind of talk about the two of them somewhat together. Okay, but this basically, if you want an interesting and slightly different treatment of this, go read chapter 5 of reconfigurable computing. And then you can fill out the questionnaire and get credit for that. So a very general compute model, like way of just thinking of describing computation, is something called communicating sequential processes, okay, or CSP. Okay, so what is CSP? How does it describe computation? So it basically says I've got some computation that occurs serially. Okay, so you can describe a serial chain of events, things that you're going to do. But you don't do that just in one process. You can make multiple processes. So here I'm making 3 different processes. Each of them will execute serially within itself, but they communicate with events. So they can send messages to each other. Okay, so I've got events passing messages to each other. Okay, and they don't all have to communicate, but some of them are going to send events under certain circumstances to each other. Okay, so this turns out to be, well, what do you think? Is this powerful? Do you think we can describe most ways of computing with this? So what do you think? This is where I'm going to stop and I'm going to do a check to see if anyone's with me, because otherwise I feel sad, right? I feel like I should just wash the board for a while and take pride in that. So what do you think? Does this seem pretty general? You can describe most things with it? Yeah, so it is pretty general. So let's just take a serial C program, okay? I don't know how to thread anything. I'm happy if I can just make my C program work. Can I describe it in this model? What do you think? Yeah, it basically would just have one process, okay? What if I had a multi-threaded software program? So I've got multiple threads communicating. Can I describe it? Yeah, I see people nodding their heads. So yeah, I would describe multiple processes. Maybe they're all doing the same thing. Maybe they're doing different things, and they're communicating with events, right? Those events might be messages. They might be, locks. So maybe one of these represents a lock process. I could describe that. I could describe multiple servers computing that way. What about hardware? Can I describe, so those were all kind of like processors. What about hardware? Can I describe hardware this way? I see somebody saying yes, right? So you think so? Yeah, you can. In fact, does this remind you of anything? Like this style? What do you think? Yeah, it reminds you of high-level synthesis, and I would say in general of hardware description languages. This is the model that Verilog and VHDL have internally. They have process in VHDL, an always block in Verilog. That's one of these things, okay? It starts at the top, goes to the end, and then they communicate through events, which are basically signals between them. So this is actually the model that HDL simulators use. And it turns out that model allows you to describe pretty much any hardware. So this is very powerful. Whoops. And in fact, so this was invented by Tony Hoare, now Sir Tony Hoare. He won the Turing Award for this. Okay, so it was considered very powerful by the research community. Anybody know what else Tony Hoare came up with? See if you know any names from computer history. So think of sorting algorithms. What's the most famous sorting algorithm you can think of? Insertion sort. He didn't invent insertion sort. So good guess, but not that one. Another ones? Nope, didn't invent bubble sort. So nobody gives a prize for bubble sort, right? So bubble sort's slow. So think of a fast sorting algorithm. Yeah, so he invented quicksort. So Tony Hoare's a very smart person, actually. So there's certain people where you go, like he already won the Turing Award. Like, wasn't he tired? Like but he still invented quicksort. I can't remember if he did it before or after. So very successful computer scientist and engineer. So it's very powerful. So, but we don't want to stop here. You could say, well, that describes everything, we're done, right? We have a compute model that's sufficiently powerful. The problem is when you're trying to make hardware, this gives very little guidance. Essentially, pretty much anything, I think anything you can write in Verilog would fit in this model. So it doesn't really guide you how to organize a computation. So it doesn't give you guidance in reasoning about a system or organizing. Okay, so what we're going to do instead is like that model is kind of underlying pretty much everything, and we could just use it, but we're going to use a different approach now. We're going to start with like basically very restrictive computation models because they're not nearly as general, but they give you a lot of insight about how you would organize your hardware. And generally, if you can use one of those restrictive models, your computation is efficient. Right? The simplicity of the model means that the hardware that implements it tends to be simple. But not everything, can be computed with such a simple model. So we're just going to start with some very restrictive models of computation, but they still let us solve important classes of problems. And then we'll gradually make them less restrictive. Makes them more generally applicable, but does cost extra hardware. So in general, kind of the heuristic that I'd adopt is it's a good idea to use the most restrictive model. That you can. Okay, so, but no more restrictive than that. If you can't describe your computation in it, well, that's too restrictive. But if you can live with those restrictions, then probably you can build a system that's easier to reason about, has more efficient hardware. Okay, so one of the ones we talked about last week was this streaming data flow model. Okay, and we saw that that one maps well to spatial hardware. Okay, and what it was again, we have a stream of input values. We're going to register them, so they're all aligned to a clock. They can go through some hardware unit that implements an operator. We can compose these operators, so the output of that could go to another hardware unit, and eventually we're going to go to another register, and that's going to give us our output stream. Okay, so there are actually a lot of variations of this streaming hardware style. And the simplest or most restrictive one is called single rate. Synchronous data flow. Okay, so we'll call that one A. There are enough of these compute models, we'll give them letters. Okay, so in this model, these operators don't change. So they're going to do the same thing forever on whatever data comes in. So they have static operators. And also the data comes in at a certain rate. It flows out to this operator, to the next, et cetera, all at the same rate. So data is going through all this stuff at the same clock frequency, same bus width, so it's the same rate. Well, I guess the bus width could change if the precision changed, but basically the number of operations or stream tokens that pass through every one of these is the same. All right? They're all working in lockstep. Okay, so data flows through all these operators at the same rate. Okay, so good things about this is it is efficient in FPGAs. Right, we already saw streaming is pretty efficient in spatial hardware. The fact that these operators don't change is very helpful for FPGAs. Remember, FPGAs, we configure them, and that takes a while, maybe 100 milliseconds. So it's nice for, which is a long time, computer hardware times. So having these be static and always do the same thing is beneficial. We can apply some optimizations that can make this even better in hardware in general, and FPGAs in particular. So one of the really good ones is we can pipeline it. Okay, so we can pipeline to increase, basically increase our parallelism, which will increase our throughput. All right, so let me erase this. So for those online, how well can you read the chalkboard? How well is it showing up on the live stream? And just type it in the chat, and Amin will tell me. So, see if there's any brave people who said what they can see. Okay. All right, so for those online, can you see the chalkboard okay on the live stream or not? It's part of why I'm actually erasing the board. First year we did this, we found you have to have a high contrast if you're going to video it. I also ran out of special super fat chalk, so we'll see if you can see it. Hopefully you can read this. And I think at least one brave soul has actually said something. So, Zoom is very blurry. Yeah, don't watch it in Zoom. Look at it in the live stream. So if you're actually using Zoom, the live stream, which you go to from the course website, will have much more clear video of the chalkboard. Zoom compresses video a ton, right? Down to something like 320 by 200. So you can't see a chalkboard on it. So try that if you're having trouble. And I'll try to get the giant chalk back and see if that works better. Okay, so we can pipeline this to increase parallelism. So let's take that operator F. Okay, so let's say that operator F, remember we said that you can spatially compose things. So maybe we look inside of it, and it's actually made out of some sub-operators, right? So these could be multiply, add, they could be something more complicated, they could be an exponential. But we'll just call them F1, F2, F3, and F4. Okay, so 4 subfunctions that together make this overall function f. And they've got a certain pattern of data between them, right? So f1 feeds f2 and f3, f2 feeds f3 and f4, and so on. Okay, so pipelining is a really good technique to gain parallelism by basically having multiple things being worked on at once. It doesn't take very much area in FPGAs because registers are so plentiful. So, but it's a good design practice to just write things in a simple way, get them working. So I've written this operator without pipelining, no registers in it, and now I want to make it faster, so I want to pipeline it. And again, that's a good philosophy, and in assignment 1, we've given you a working system and told you to pipeline it, so we're actually kind of making you follow that style. Where can I pipeline this? Okay, so where can I put registers so that this is pipelined correctly? Okay, I can't just put registers anywhere I want. So some choices are legal, meaning they won't change the output. Some are not, and then some can be better choices than others in terms of efficiency. So, so what do you think? Does anybody think of where could I put a pipeline register? Could I put one here at the input? Yeah, I could do that. Could I put one at the output? I could do that. Okay, so the easy ones that are not maybe the most useful, because most of my delay is probably in here, but those ones would work. Yeah, what do you think, Alex?
I want to put one between F1 and F2. But then you have
Okay, so putting one there. I'll put dotted in. It's not a knock against you. We're just being careful, right? Maybe we got to back out of this. So okay, so you put one there.
you have to be a bit careful because then you want to put one after F2 at both edges.
You want to put one after F2 at both edges.
Yeah.
So you want one there, and you want one here.
Yep.
Is that right? Okay, so we'll put one there as well. Okay, so here, here, here. Is that right?
That's a weird one. I think you need to put 2 registers between F1 and F3.
2 registers between F1 and F3. It's a very complicated pipeline. Let's see. Okay, we're going to go with it, and then I'm going to see if I can figure out if it's correct after that. Okay. So. Okay, where do you? You want one over here?
Might as well, yeah. We're already there.
Okay. Okay, so you got it there. They are plentiful. So maybe we'll just put one over here for good luck. So, okay, so what do you think? So you put 1, 2, 3, 4, 5, 6 registers in here. Okay, so I actually have to think about this, whether or not this is correct. I think it might be. No, I think it's not. Sorry. Okay, so okay, it would be the nice thing about what you've done is there are a lot of registers in here, okay? So you actually don't have any long paths. Before you put them in, I had a path that went all the way through here, here, here. I had a path that went through all 4 of these operators with no registers on it. Probably going to be my critical path. It's going to limit the clock frequency of my design. Kind of annoying. Okay, and with the registers, that doesn't happen anymore. So from an efficiency point of view, looks pretty good. But now let's talk about correctness, which is important, right? So what's the rule for correctness? So there is, there's a rule for how you could pipeline. Yeah.
We actually need to come up with a graph first, and if we want to actually put a register on one of the edges, we need to come up with a cut that goes through that and we have to add registers for other edges that outputs.
Yeah, okay, so I'm just going to repeat that for those online who might not have heard it. So you said they're basically, you have to find a graph cut, okay? And so it's not okay to just kind of, there's a method to this. It must be a cut. Draw a cut that disconnects my inputs from my outputs. And I have to, every edge that I cut, I need to put a register on, okay? So yeah, that is a good solution. So I'm going to write down the basic, okay, so the most basic rule, this is like the fundamental one, is basically all input to output paths in this circuit, must increase latency by the same amount.
So you wouldn't take your longest path and just try to make it quicker?
That's your goal, okay? But, I mean, I could do that, let's say I'm going to erase this one, right? Actually, I don't think I will yet. Let's say I just want to make my longest path faster. So that's my goal. So I put a register here, 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 done, right? My longest path is cut up. However, my circuit, you'll find, does not compute the same thing, okay? It doesn't compute the same thing because if I take, for example, F3 used to take, I send one input in, I compute some transform of it, goes here, gets transformed some more, and then that intermediate result and this intermediate result for that same input get combined by this and move on. If I just stick a register here and a register here, I actually have, this is processing the data from 2 clock cycles ago, which is like a completely different input, and it's mixing it with the data from the most recent input. That's just a different answer, okay? Like I wasn't trying to do that. So the most fundamental thing is that all of these paths from my input to the output, it's okay to change their latency. If I start putting registers in here, I will change their latency, but all the input to output paths have to go up in latency by the same amount, okay? Which means that basically means I'm still computing on the same inputs in time that I used to be. From the outside world, all I can observe is that the latency in terms of clock cycles of this circuit has increased, okay? But the sequence of outputs it produces are the same. They may come out 2 cycles later, 3 cycles later, but they all come out in the same order and in the same value. And generally, people don't care very much about I added 2 cycles of latency, especially if I then increase the clock frequency, okay? Like the downstream logic is fine. It just wants the sequence of values. So this is the fundamental rule, but this rule leads to one that's actually easier to apply, which is exactly what Sohail just said. This means that if you find a directed cut, okay, it's actually a directed cut because you need to have all the edges going across it in the same direction, okay? Like the cut has to disconnect my inputs from my outputs, okay? So you get a directed cut that divides inputs from outputs. Okay, so does that make sense? Yeah.
So is that why when you put one between F1, F2, one between F2, F3, one between F3, F4 didn't work because that cut had 2 directions?
Yeah, so let's see. I'm going to do it. This one I can tell doesn't work because I can trace the paths and I can say their latency is not all the same. Okay, so I'm kind of applying the fundamental rule of it doesn't, like this path, if I go through here, I added 2 cycles of latency.
The example you did afterwards, you said you were going to erase it.
Oh, okay. So I'm going to talk about this one for a second. So if I use this fundamental one, you go, okay, this path, here's my input. I'm going to write this. Input, here's my output. If I take this path up here, I added 2 cycles of latency, right, with the Alex pipeline. If I take this path, I go 1, 2, 3 cycles of latency. Okay, that doesn't match. If I take this path, I get 1, 2, 3. Okay, so that's 3 as well. So I matched some of them, but I didn't match them all, which means that in some of these intermediate calculations, I am mixing data from essentially different clock cycles in a way that I shouldn't be doing. Okay, does that make sense? Okay, so let's draw. I'm going to draw this again and apply this directed cut technique. All right, so I've got F1, I've got F2, F3, F4. Okay, so let's take this. Let's put a cut line there. Does that, now what we do with these cut lines is if this cut line passes my tests, I would put a register on every single edge, communication that it's cut. So does this pass my test? What do you think? Okay, so I see thumbs up. Yeah, it disconnects my input from my output, and it's a cut, right? It went through all the, it disconnected them. I mean, that's the definition of the cut. After I cut all these edges, there is no way to get from one side to the other. It also, if I say this is the input side and this is the output side, all my edges are crossing in the same direction, which is actually another important rule, okay? If I had this edge crossing the other way, so I have like some things going from the input to the output side and some going backwards, that's actually not a valid cut either. So I also have to check that. Okay, but this one I would put in a register there, I would put in a register here, and I would put in a register here. Okay, that matches my cut. Let me go now apply my fundamental test of latency. And if I've done this correctly, I'm going to pass the test. So if I go this way, I got 1 extra cycle. If I go through here, F2, and then down to F3, I've also got 1 extra cycle. If I went F1 to F3 to F4, also got 1 extra cycle. So it passes the latency test. All the paths that I can find in there went up by 1 cycle, which is good. Okay, so I passed my cross-check. This isn't the only cut, and I can do this multiple times, right? So maybe this will make my circuit faster, right? My critical path is probably now F1 to F2, or maybe F3 to F4. But that's better than it used to be, where it went all the way from F1, F2, F3, F4. Can I pipeline again? So no reason not to, right? So I could say, okay, let's draw another cut here. And I can do that now. I can keep my old pipelining, and I can put another one in. Put another cut, put more registers. That also works. I could put another cut here if I want. Okay, so put that there and that there. And all of these are legal. I can do them all. And now basically my critical path is down to 1 operator. And in a more complicated circuit, this can be more challenging to do if you don't kind of follow a procedure like this, right? Like start with a simple circuit and then start finding cuts and pipelining them. It's also useful even if you don't do it in a sort of very determined way. Just keep this in your mind. Okay, so does that make sense? Okay, so here I put all sorts of cuts in, which is not a bad idea. Let's see. If I just had to pick a certain number of cuts, like I might not want to put every conceivable cut I can think of. That might be so many registers that it starts getting expensive, even in an FPGA, which have a lot of pre-built registers. So we now know how to find legal cuts. What cuts do we kind of want? Which ones are the most useful for us? So what do you think? I did 3 cuts here. If I told you you didn't have enough registers to do all 3 of them, or it was going to cost you some area, is there one of these that you would do before the others, or do you think they're all equally good?
Probably want that diagonal one first.
Yeah, then I'd do the diagonal one first too. Why do you like that one the best?
More registers.
So more registers is actually not good. Okay, sorry, but like more. So the more registers means more area. Okay, well, or more risk of running out of registers. So the registers themselves is not great to get more, but this still is the best cut in my opinion. Why is it better? So you're close. You're very close. I might be misinterpreting you. So what do you think? Not 100% sure? Yeah, what do you think?
It reduces the critical path. So if we do the first one, we still have F2, F3, F4 to go. If we do the last one, we still have F1, F2, F3. But if we do the diagonal one, we just have F1, F2, or F3, F4.
Yeah, exactly. So this first cut, kind of like my bad critical path went through all 4 operators. And this first cut chops it in half, right? 2 on one side, 2 on the other. The other 2 cuts I showed would put, well, this would put 1 on one side, 3 on the other, and also 3 on one side, 1 on the other. Okay, so you'd actually like cuts that kind of bipartition your logic, well, that cut the critical path in half, if possible, okay? Because that has the potential to double your frequency. So equal logic on both sides is good. The other thing that you'd actually like to do is you'd actually like cuts that don't cross many of these edges. So sometimes you can wind up with like a cone of logic where it has both wide parts and narrow parts, okay? And it might be many levels deep. If you put a cut where it doesn't cross many edges, then you don't have to put as many registers in. Okay, now in this case, the ones that don't cross as many edges also don't divide my critical path very well, so I probably don't like them as well. But there can be cases where you've got multiple choices that would divide your critical path pretty well. And some of them are going to cut a lot of edges and some a few. So the ones that cut few edges are better because they cut fewer registers, or they make fewer registers. And then it's not a either or in some cases either. Like here, probably it's reasonable to do all these cuts. As long as I don't run out of registers, I'd probably do them all. Okay. Okay, so let me draw something else. So let's say I've got a stream of inputs. Okay, so in streaming, when I say input, let's call this x, and again, it's a sequence of values. And let's say I go through some operator f1, then I go through some operator f2, then I register it, and that's going to be my output. Okay, this is called a feed-forward system. All the data just keeps flowing forward. There's a direction to it. Not all systems are like that. So let's say in this system that the output, this register output, also feeds back into the system. So in signal processing, it's again an important application of FPGAs, there are 2 big classes of filters. So one is a finite impulse response filter, and it actually is feed-forward. Okay? Another one is an infinite impulse response filter, which actually incorporates feedback, as I've shown here. It's not feed-forward. Okay? So there's lots of other things that have feedback too. This could be a finite state machine, could be an infinite impulse response filter. Can I pipeline this? So this circuit works. Okay, that's my design. I got the logic right. It does the right thing. Where can I pipeline this? Okay, maybe this is limiting the speed of my design. Okay, I've got a critical path that goes, basically from this register output back through here. That's my design critical path. So I want to make it faster. I've learned about pipelining. I'm very excited. Very excited. I want to start drawing cut lines. I want to put registers in. Where can I pipeline this to make it faster? What do you think? No one wants to take a shot at it. So, what's that? Okay, so you want to try putting it here. So that seems like, from a point of view of balancing the critical path. My critical path is the delay that goes all the way around here. It's kind of right in the middle. Seems like a good place to put it. It's it's whatever bus width this is. So if it was 1 bit, it's 1 register. If it's 32, it's 32 registers. So it seems pretty good. So maybe I could put a register here. Okay. Let's do my cut test. If I do my cut test, draw a cut across there, I basically can't really I can disconnect inputs from outputs. Well, this disconnects the circuit, but I'm basically crossing this cut line in both directions. Once from input to output, once from output to input. So it's like failing my test of directed cut because I'm going across this cut line in 2 directions, and I shouldn't be doing that. Okay, if I take my most fundamental test of did I change the latency of any paths, or did I change them all equally, it also fails that. And maybe the easiest way to see that is the original circuit, let's say without this register, what it computes is y of I is equal to f2 of f1 of x of I. Okay, so hopefully pretty obvious, right? I'm just writing this in a mathematical notation. Once I put this register in, okay, I've got, actually I have it's F1, this is actually not so obvious because I screwed it up. F1 has x of I and y of I minus 1. Okay, it's got the previous output and the current input. All right, and that's what's going to produce the current output. Does everybody agree? Okay, so that's what that did before I put this pipeline register in. Once I put this pipeline register in, I'm actually, this is basically x goes in. Actually, I always screw myself up on this one. I think I should have put the register there because it's easier to write the math. Basically, I'm going to wind up with, it takes me 2 cycles for this data to get there, okay? So I'm going to take x of I, and I'm going to compute y of essentially 2 cycles ago, okay? And I think that mathematically, if I write this out, I'm going to screw it up. I think if I put it here, it's probably easier. So I'm going to move the pipeline register there. It doesn't actually change the incorrectness of it, but it makes my notation easier. So let's try that. So basically, if this was y of I here, this is y of I minus 1. So now I'm basically I'm taking x of I and y of, so if I had the old y, it's y of I minus 1. That's a y of I minus 2. So I've got y of I minus 2. I take f1 of that, and then I take f2 of that whole thing. And that is my new y of I. Okay, so it's broken because instead of taking the previous output and using it in the current input to compute the next thing, I'm taking something that was 2 cycles ago. Does that make sense? And yeah, I cheated and moved the register because it just makes my notation easier because I realized I was probably going to get confused with the variable names otherwise. But it doesn't matter whether I move this register from here to here. I still get the same problem. Okay, so does that make sense? So loops are a problem, right? You actually try to avoid loops in hardware when you can because they can't be pipelined. So they do tend to be speed limiting paths. You try to keep feedback, limited, because if there's a lot of logic in a feedback loop, it limits your speed. We'll see another optimization that we can do that can help with this sum when we get to another compute model. Yeah?
So is there physically no way we could have a pipeline register between F1 and F2 then?
Physically, you could do it. It's just logically, it's incorrect.
So it will always be
it will always be logically incorrect. There is no place, like if my original design was this was correct, that is my logic I want, there is no place I can put registers, no sequence of registers I can put in that just allows me to clock it faster and gets the same output. Now, I might be able to go in and say, maybe I can just rethink this whole thing, right? And get rid of this loop or shorten the loop. So I might be able to go in and rewrite the logic, but there's no structural transformation that I can do. Like what we did before with the cuts was, I don't actually even have to understand the design. I can literally get like a drawing of the design and I can start pipelining it. And I'll just apply rules and it will be correct. I cannot do that on this loop. Any set of pipeline I put in here is immediately incorrect. Does that make sense? Yeah.
In loop, can we still pipeline the individual operators like inside F1 and F2?
You can if that's how you originally made it. So I guess basically what I'm doing here is like F1 and F2 are kind of black boxes. Somebody made them, and it passes the test bench. Okay, like often hardware design, just like software design, it's iterative. You get something simple working, and you try to make it faster if it's a problem. So somebody's made this work. The logic's correct. If inside them it has a couple of stages of pipelining and it's correct, it's fine. You can leave that alone. But if it's correct without pipelining, I can't keep it correct and just put pipelining in to make it faster. Does that make sense? So they're a bit of a pain. So I know at least Intel's CAD tools, because their architectures are so focused on allowing deep pipeline, their CAD tools will even tell you about loops in your logic. They'll say, this loop is limiting your speed. I can't fix it for you, but maybe you're a really clever engineer and you could go off and rewrite it, right? So they have advisors that will give in their tools that will give you information on that. Okay, so let's go through maybe one more. Go through a couple more, or one more variation on this data flow, and then maybe we'll take a break. Okay, so I use that kind of as a digression in how you pipeline well, and this style of computation is really nicely suited to pipelining. But this compute model is still pretty limited. Okay, it's pretty limited because we basically said data flows through everything at the same rate. Okay, and it has to do that. Okay, so let's try to remove that assumption. Okay, so still a data flow or streaming architecture, but it's a little more flexible. So in this design that I've been showing you, it can't handle it if some of these operators produce more output than their input. Okay, because we have all of this kind of has to flow through without any stalls, any changes in the rate of flow of tokens through the network. Okay. Okay, so this is a very simple thing. Like I just got an operator that produces more output data, like more tokens or data items than are input to it. What would be an example of that? Well, from signal processing, a simple example is an interpolation filter. Well, all an interpolation filter is there's some waveform coming into my signal processing system. I've sampled it at a certain rate, and I now want to basically produce samples in between. Okay, so an interpolation filter says I got to do some fine-tuned processing. I actually want to interpolate and get more samples. I'm going to up the data rate. Or we can have less output than our input. Okay, so we can have the opposite thing, and the obvious one for that would be a decimation filter in signal processing. Okay, decimation filter is just the opposite, right? I've got all these signal samples. I decide it's too much. I don't need that level of detail. I want to drop every second one. Okay, so let's get rid of that one, et cetera. It's good enough for the next phase of signal processing. Okay, so these are pretty common. You can go with lots and lots of examples of this, but they mean you can't run everything at the same rate. The hardware I showed here is just everything's running in lockstep. It actually can't handle this simple problem. Okay, so it can't run everything at the same rate. So what do you think we should do? The solution is actually like not very hard. It's pretty elegant. What do you think we should do? So okay, here's my idea. Maybe I'll have some control logic that keeps track of the fact that F2 produces twice as much output as F1, and it activates F4 at the right rate, and then we figure out how often F4 is producing stuff, and we'll have an enable signal that activates the downstream logic at the right rate. What do you think? Do you like my solution? No one likes this? It's a bit vague. Okay, so it'll be like some kind of centralized control system, right? I'll make some centralized system that figures out when are various operators producing valid data, and let's try to ignore some, and so on. That's not a good idea, okay? The spatial hardware is nicely distributed without sort of centralized control. It makes it faster because you don't have long delays, and more importantly, makes it easier to design. So you don't want to start going, I'll have some centralized control that figures it all out. Yeah, what do you think, Alex? Close. I think you're actually on to the next thing. So that's probably like, we are going to go on to, this is going to solve a bit of our problem, but not everything. So yeah, we're going to go into things that use exactly that. So you're thinking a shift register or a FIFO might help with rate imbalances. Hold that thought. So it's given another name. It's the next one after this. So yeah. You could do multiple clocks. It is kind of a mess though. Like it only works if things are, if it's like if they're forever producing things at the same multiple of each other. And multiple clocks are harder to design with when you have things communicating tightly. Okay, so there's a possible solution, but it's not the one we're going to use in this data flow architecture. So the solution to this one is actually pretty simple. Let's see. Well, it's simple once you see it, at least. Let me erase this. See. All right, I'll draw an even simpler data flow network. You got F1, F2. They're going to some operator G. Goes down to something else. Basically what you do is you tag your data. Tag it with a valid bit. So we already had data. Wherever we had a data bus, so maybe this was 32 bits of data, maybe it was 128. Often data paths are pretty wide in hardware. We're processing a lot of data at once. We put one extra signal, which is not very expensive. Okay, it would be expensive if data was 1 bit wide, but again, it's usually quite wide, 128 bits, well, at least 16, but more commonly 128, 256, etc. And we do that everywhere. Wherever we had a data signal, we now put, or a data bus, we put a valid bit on it as well. What does this do? Well, this G function basically checks, do I have valid data on both my inputs? And if I do, I mark my output as valid. Okay? If I don't, my output is invalid. Every single block does this. And what happens now, your valid bits just propagate naturally through the network. So all of your data is tagged. Are you valid or not? There's no centralized control. It's just basically a local decision at each operator. Check if your 2 inputs are valid, or 3 inputs, or 4 inputs. If they are, your output's valid. If they aren't, your output is invalid. You just wait. It naturally allows We could send 1 unit of data into here, and this might produce several units of data. It's fine. Or we could send 4 units of data in here, and this only produces 1 output. That's fine too. Okay, you'll just get multiple clocks where they're just not marked valid. We can still clock everything at the same rate. Pipelining is still easy. So this is now both data and valid bits, but if we want to pipeline this, we draw a cut, and we put pipeline registers in here. And we just pipeline both the data, like our real data, and our valid bits, and it's fine, right? Everything lines up in time. If I want to do more pipelining, I put another cut here, put a register there, it's all fine. It's just wherever I put like a cut, it will always cut my data bus and my valid bit. I pipeline them both exactly the same way. They stay aligned. Okay, so this is also, it's often given the name feed-forward control. Okay, basically G executes when both of its inputs are valid. And now I still have, in this system actually allows me to have essentially some dead cycles in my data for whatever reason. G still, whenever the data is valid on G, it's only going to be there for 1 clock cycle, right? So F2 produces something, puts it here. F1 produces something, it's there. They're both valid. G must basically grab that data and start and produce its output, okay? If it can't keep up, let's say it actually has to produce 4 output items, we have a problem, right? Because it has no, the reason we have a problem is F1 and F2 are probably just going to keep producing data, and they're going to overwrite its inputs. But it's still working on the last stuff. So this solves one of our problems. We don't have to have data going at the same rate all the way through the network. But we still have to make sure that essentially the downstream logic can always keep up with the upstream, okay? Because it has no way to say, I can't take it anymore, stop. So we have to choose the speeds of F1, F2, and G here, such that we never drop data. Well, no valid data is dropped. What that means in practice is the downstream logic always has to be able to keep up with however fast the upstream logic can produce data to it as the maximum rate, which again can be limiting. So we'll take a break now till, how about till 5:35? So take a 10-minute break. And then when we come back, we're going to need Alex's idea, okay? Because part of what we're going to do to solve this is we need to put some memory into here. Hey.
Hi, thanks for having me. I have a question.
Yeah.
How is the last thing is different than asynchronous logic? Conceptually, I understand there is a clock, but I mean.
How is this last thing? Which thing? This part or?
With a different rate.
How is it different than asynchronous? I guess because it is all quantized to a clock. too dark. Sorry. There's like a long time lag, right? It's like playing a video game with a super bad controller. Okay. We're going to get going again, but first I'm sure you're wondering what the course survey results. Okay, so let me click on this. So, and hopefully this will bring it up quickly. Okay. Okay, so mix of different degree programs. Lots of MEng, as you might expect. The MEng program's gotten quite big, mostly full-time, but a lot of part-time, people out working as well, often in the industry, and quite a few MSc and several PhD. So pretty good mix of different students. And whoops, what happened there? Maybe I need to arrow. Okay, thank you. Okay, so for the fraction of people, this is a minority of the students who are working. Where are they working? Actually, all sorts of interesting places, actually. So it's kind of interesting how these word charts work. I think that's advanced micro devices, not micro devices advanced. But yeah, multiple people from Synopsys and Intel and AMD and also General Motors and other companies. So that's great. So actually, that's really, usually I found in this class it's really interesting when people bring an industrial perspective and go, hey, we hit this in my job. Primary research area, it's kind of all over the map. Like this computer architecture was actually selected by 5 out of 44 people. So it's actually, it shows super big because I think it just goes, that's the most popular response. But you see lots of different ones. So embedded systems, machine learning, hardware accelerators, and general computer architecture. So all sorts of different stuff, design automation, hardware description languages. So some people know more than one. So Verilog and System Verilog, which again are really one language, is the most popular. VHDL also popular, and some people said there's some other one. And there were a few people that didn't get counted in this because they don't know an HDL. You can pick it up, but go do your reading starting right away, right? Again, you don't have to be an expert on HDL in this course, but you want to know some of it. Probably about 20% of the students actually know both Verilog and VHDL. So there's some bilingual people. Are you taking, so it's helpful but not necessary at all for you to know how CAD tools work. So about 27% of the students are taking Jason Henderson's course on CAD tools for such the back end part of the flow for digital circuit synthesis and layout. So you don't need that knowledge. Knowing that most students don't have it, I'll make sure when we talk about CAD tools, I give a bit of background. It's not the primary topic of the course, but you can't fully separate FPGA architecture from CAD tools. Let's see. Do you know how to design digital's logic at the gate level? Most people know how, not everybody, which is okay. You'll learn some about it in this course. Transistor level is about half and half. We'll do some transistor level design, but it's all digital, so we can basically estimate delay and area. So I'll teach you how to do it. At the end of this course, you should know something about transistor level design if you didn't at the start. I don't assume you know how to do it to begin with. And most people plan to attend class in person, and a few are not quite sure. So it looks like we've got a fair number of people online again today, so we'll keep doing the live streams. It also means if you're like, you can go back and look at the videos after the class. So I'll post those as well. And this is the word chart is not super, so I like trees. That's why I asked this question, because I actually am genuinely curious, and I also just like talking about trees, and it's hard to integrate them into the course otherwise. So yeah, the word chart doesn't tell you that much, except tree was the most common word. And there's a diversity, so of what else people are doing, what other kind of tree they like. So let me go back to the slides. Let's see if I can get back to where I was. Okay, so I also went and looked at the Excel file so I could summarize this better than the word chart. Okay, so everything that's bold, in case you're curious, like, hey, what kind of tree do my classmates like? Everything that's bold, more than one person picked, and they're in descending order. Okay, so oak, pine, maple, palm, redwoods and sequoias, tall. Some people just like tall trees. And then at least like one of each. And then actually the last two where people use their scientific names. So I actually knew the scientific name for this one, but I learned the scientific name for that, so I learned something new. And then about 20% of people, so 80% chose biological real trees they've gotten outside sometime during grad school. 20% are just completely engineering, right? So binary tree, decision trees, max heap. So they've given up on biological trees in nature, and their favorites are in algorithm textbooks. Okay, so my favorite tree is the giant sequoia, right? And redwoods. These are both from the same family. So this tree is General Sherman. It's the largest living thing on Earth by like just a single organism. It's not a clone. It's 3,000 years old, 275 feet tall. It's 37-foot diameter around the base, and it weighs, they estimate, they haven't actually weighed it, but 4.2 million pounds. So it's kind of an amazing thing, actually. So it's in the Sierra Nevada mountains. If you go to Silicon Valley, it's about 4 hours to the east. And the other related kind of tree are the coast redwoods. They're from the same general family. They're even taller, so 370 feet tall. So it's like a 37-story building. They're not quite as wide, but they're taller. And these ones are basically, you can get to them an hour north of San Francisco. So many of you during your graduate career or afterwards will wind up going to Silicon Valley. My advice is forget going to look at like, you know, Apple headquarters and stuff. Go look at the giant sequoias and the redwoods, right? So they are really cool, actually. So, okay, so that was not super relevant to the course material, but it's, I wanted to do it anyway. And that's one of the advantages of being a prof, is you can do a few things like that. So, okay, let's see, where did I put this? Okay, so before the break, I said, okay, we need to get even more general operators or data flow styles. Okay, so we've gone, this is our third one, okay? And you notice there are variations on streaming. Streaming is very powerful in FPGAs, so we're talking about it a bunch. So the next one's called dynamic streaming data flow. This is a bit more general still. Basically the problem it solves is, what if my time to produce an output varies? Okay, so an example, there are many examples of that. You can think of lots of hardware where maybe I'm accessing off-chip memory, which means maybe I get a hit in my in the row, or maybe I have to do a row and column access. So maybe my time varies because there's off-chip memory and it's in a refresh cycle. It's just not as deterministic. It can be algorithmic. So an algorithm that I think of here would be Newton-Raphson iteration. How many people remember what Newton-Raphson is? Do you ever remember that term at all? It's an approximation technique you learned in calculus. Okay, it's an iterative approximation technique for a function, and it fundamentally, for some functions, converges very quickly, and for others, less quickly. So this might be something where it just sometimes takes 5 steps, sometimes it takes 12 steps to get an accurate enough answer. So that means you don't know exactly how long it's going to take to produce the next output. What if the amount of data that you output varies? So you've hooked together all your operators, but sometimes they produce more data than others. So this is a bit different than an interpolation or decimation filter, where one might produce more data than other, but it's deterministic. You know, this one always produces half as much data as its input, or twice as much data. Can you think of an example? There's lots of examples of this, but examples where the amount of data varies. And there are lots, right? So you can come up with all sorts of algorithms. But I can give you a fundamental one. Let's take compression. Okay, so one of the most popular compression algorithms is Huffman encoding. Basically looks at how common various symbols are in your data stream. And the most common ones, it assigns short bit sequences, and the less common ones, it assigns long bit sequences. Send it a bunch of the common signals, and it doesn't produce very many output bits. Send it a bunch of uncommon ones, and it produces a whole bunch. So it's, again, fundamental in the algorithm. It's not even something you can get rid of in hardware. Okay, so for these reasons, like there's lots of reasons why we may not be able to bound exactly how long it'll take our computation to send out some data, or how much data size it might output. If we could worst case it, then we could say, well, we'll always produce data in no more than 12 clock cycles. We'll never produce more than 20 bytes. You could basically worst case everything, making sure that every operator hardware was sized for that worst case, but that could be very inefficient. And in some cases, you might not even be able to find like any reasonable bound. So what do you do? So actually, Alex already mentioned what you do, basically. So what you need to do at this point is introduce some memory elements. You need to allow some flexibility in this pipeline. You put some memory elements in so that you can deal with short-term surges of data, okay? So that's part of it at least. So what we're going to do is we're going to convert some of these pipeline registers to FIFOs. Okay, so first input, first output buffers or queues, and that allows us to decouple the operators. Okay, so if we've got a limited amount of computation and balance, this might be enough. We just allowed some buffering, so there's a burst of data. We have a big enough FIFO to store it. But if it's, what if that F2 just keeps producing lots of data clock cycle after clock cycle and G can't process it fast enough? Eventually, a buffer in between would fill up. Okay, so buffers by themselves, well, maybe I'll draw this, but buffers by themselves aren't going to be enough. But let's draw what we've got so far. So we had F1 and F2 feeding G with just registers, and now we're going to change that to, they have a FIFO. Okay, so I can tolerate now some imbalance of this produces a big burst of data. This can absorb that data, and G can gradually work on it. But I already told you, like, what if it's, and if we can't bound this, if that could happen over and over again, eventually this buffer is going to overflow. So it's not a full solution. What else do I need to do? Yeah.
Feedback from the FIFO.
Yeah. So I need to do have feedback from the FIFO, also, which is often known as back pressure. Okay, so the FIFO is to absorb a burst of data, but when the FIFO is going to fill up, we need to say you got to stop, okay? And so that we don't start losing data. And I need to do that everywhere. Okay, so this FIFO needs to back pressure this. Maybe G, whatever's taking data out of here is not taking it out fast enough. So we need G to have a back pressure signal. When should we assert this back pressure signal? Like when the FIFO's full, kind of, right? Is it good enough to assert it when it's full? Yeah, if we assert it when it's full and this produces one more data item, we're going to lose it, right? We have no place to store it. So we actually want to do it a bit sooner. So we want to assert this when it's nearly full, okay? Now, if we could actually still use, and we commonly do, have pipeline registers inside this operator. Okay, so there's no reason this has to be combinational. In general, it won't be. Still a good idea to pipeline this. So if G takes several clock cycles to produce its output after it decides that it's got two new inputs, we need to actually assert this several cycles early. Okay, so we need to, this is basically got to assert when there's still enough room in the FIFO that if we stop this from taking any new data and some stuff still drains out, it won't overflow, okay? So if this stops immediately, then we just need one extra spot. So we could check for, we assert this signal when there's only one more spot left. If this takes several cycles to drain, because we pipelined it with regular registers, then instead of one, we might have to be 5 cycles early or so on. Does that make sense? And that would mean we'd probably need to make our FIFO a bit bigger too, because we want this FIFO to be big enough that under normal operation, it doesn't fill up, right? We really don't want this back pressure signal to activate very often. Does that make sense? Let's see. So we've got to do two things. We basically also add back pressure. So this is a very popular data flow style. Is everybody with me and they understand how this works? Make sense? Okay. And you do mix them. So I started off with the simplest data flow, the single rate streaming data flow where you couldn't stop things at all. Inside G, I likely would still use that, right? If I know once I take my inputs that nothing can go wrong, then why wouldn't I just use regular pipeline registers? These FIFOs are significantly bigger. So we tend to mix and match. It's on sort of the level of relatively big operators where this unpredictability on are they going to produce things fast enough that we bother to put these FIFOs in and the back pressure. Yeah?
In the context of routing, are the other benefits between the models for like, oh, this one's easier to route than this one, for example?
It's a good question. I mean, streaming data flow in general is easy to route, or it's hardware efficient, and it fits well in an FPGA because it's easy to pipeline deeply. There's no global state. Like notice all the state. We still have valid bits on this, by the way. Okay, so the data invalid, this adds onto them, but we still have the data invalid. And you now have this back pressure signal as well, which you'll see in lab 2 is called a ready signal. Okay, so it's kind of like the opposite of back pressure. Like, am I ready or not? So, let me think about it. Okay, so the fact that this doesn't have central state, all decisions about how processing proceeds are pretty local, right? This operator would look at its 2 inputs, see if they're both valid. This FIFO would look at its state of fullness and decide whether to assert the back pressure. That's good. You don't want to drag all your wires to one central space and then pull them all back out. And everything can be pipelined, including I can pipeline, this interconnect. I can pipeline this interconnect. When I pipeline this interconnect, remember I told you this looks like a loop, right? And I told you can't pipeline the loop. You can't pipeline the loop without thinking about the logic. Okay, so I can't just go, hey, this is what's limiting my speed. I'm just going to throw another register here and another register here, and it's all good. But I can put those 2 registers in, realize that I now need to detect this as almost full 2 cycles earlier, change my logic to say, oh, I used to need to have 1 empty space, now I need to have 3 empty spaces, and it will work again. Does that make sense? So this is a case of, yeah, I changed the latency of the loop, and I now need to go in and manually change my logic. But I can do that if I understand my design. Does that answer your question? The other thing is these FIFOs, so FPGAs are really good at registers. They really like distributed state. FIFOs, let's talk about how you build this FIFO. So actually, Alex, you said shift registers. Okay, so these are generally wide words. Okay, so you don't normally do this on like 1 bit. So let's say this is 128 bits wide. Maybe that's too much. Okay, let's say it's like 32 bits wide because I want to draw that. So if it's 32 bits wide, I could put it in a shift register. Okay, and the shift register is really 32 bits, and that feeds into another one, and so on, right? So maybe I need my FIFO to be, I don't know, I work out that I need it to be 8 words deep, given like the latency of how much pipelining I have here and inside here, okay? And maybe some of the imbalance I get sometimes. But I'm going to draw 3. And this is also 32 bits wide. So you can see this can get kind of big. The way this FIFO works is I need to be able to insert data in this shift register, and I need to get out like whatever's at the head of the shift register. So I'm going to need a mux too, all right? And this mux is going to be 32 bits wide, but it's going to let me pick any one of these things as what is my sort of the head of my queue. Does that make sense? So there's a few different ways I could build this out of shift registers, but generally I'm going to need, let's say I need an 8 deep FIFO. I'm going to need 8 times 32 registers, and I'm going to need an 8-to-1 mux, and I'll need for a 32-bit wide data path 32 of those 8-to-1 muxes. This is a reasonable amount of area. It's also, and it gets worse if you go, okay, 8 wasn't enough. I need 16 or I need 32. As the depth of this gets bigger, it starts getting expensive. It's also high power. Every time I put something in the shift register, everybody moves over by 1. Okay, that's a lot of power in a circuit, and CMOS circuits is transitions. Right? It's charging and discharging capacitance. If everybody moves over by 1, it means on average half of these nodes are going to change state, and that means half of them are charging or discharging capacitance every cycle. So that's a lot of power. So we can build it out of shift registers, but these FIFOs should only be built out of shift registers when they're very shallow. Okay, like very shallow meaning like maybe 2 words, right? Maybe maybe 3, but not a lot. So what's my other alternative for building this? Yeah. Yeah, so the way that you build this, especially as it gets bigger, is you use a RAM, and you have a little bit of logic that is basically your read pointer. So where am I going to take, when I do my read on this side, where do I take it from? And when I do my write, where do I put it? My write's going in on this side. Okay, so these pointers are basically just little, maybe if I need a buffer that's 32 deep, I have 5-bit registers. That are these 2 registers, 2 pointers. There's a little bit of logic to update them. Okay, so that's inside my HDL. And I need to have a RAM. Let's say I need 32 words. That fits pretty well in FPGA block RAM. So we're going to study FPGA architecture a little later. But basically, FPGAs have tens of thousands of RAMs that are this size. So this turns out to be, except for the smallest buffers, this turns out to be a more efficient implementation. It's also much more efficient in power. So it turns out to be more area efficient. In power, you're just writing 1 new word in the cycle and reading 1 word out. Everybody else stays where they are. For a shift register, everybody moves over by 1. All the people you don't care about. And as the shift register gets deep, that becomes a very large amount of power. So you don't want to do it that way when they're big. You want to do it this way. Does that make sense? You don't have to write this yourself. So you are going to actually wind up probably using some FIFOs, not in this assignment, but the next one. And there are IP cores in Cordis that will allow you to just ask for, this is such a common thing that you can just ask, give me a FIFO, and you put it in your design. You don't have to go write the HDL for it yourself. Okay, so yeah, this was shift register versus RAM. So RAM FIFO. And this one wins in most cases. This wins when it's very, very shallow. Let's see. I think I went on a digression. Did I answer your question? Okay, thanks. Okay, this is now we're into kind of, so this is our dominant streaming paradigm. Big operators that we can't predict, we do this FIFO and handshaking. Small ones, we just pipeline, okay, if we know that there's going to be no stalls. But we can still keep working on these streaming compute models. Okay, so we got some pretty efficient compute models, but all these operators I've shown you, like F1, F2, G, they're all static. They just do the same thing over and over again. Again, for some things like signal processing, that can be a very good match. Like the wireless base station, it does tend to just do the same thing over and over again on every single communication that's coming in. So this is not a problem. It's very efficient. But there can be cases where you want to change what the operators are over time. Okay, so, and this model allows us to do that. So we can change either the operators or the connections over time. And there's basically 2 ways to do this. Okay, so basically I don't always want to be doing the same computation. I want to be able to reuse some of my hardware but change the computation from time to time. So first method is basically build more flexible hardware. So we build more flexibility in operators. And we build muxing into the interconnect. And maybe I'll go over here. Okay, so maybe in my system I know that sometimes I want to use a certain function. Some other times I want to use a different function on my input stream. I can just build both in hardware and put a mux in my data path. And now my hardware can do either one, and I can select which one very quickly with some control signal. Maybe there's some other function F2. I always do the same thing. And it goes into this G function, which again is like what I had up there. But maybe I decide this G function also needs to be a bit more general. So I want to be able to change it. So let's say the G function I had before, let's say it was just doing a certain mathematical operation with all the time. So its input is x. It did 181x squared plus 78x plus c. Because I know what constants I'm multiplying by and adding, the FPGA CAD tools will optimize this further. They can actually remove parts of the adder, parts of the multipliers, because they know where you have a 1 and a 0 in the product. So there's some extra optimizations that can occur. So we get extra compile time optimizations. But maybe that's not good enough, right? My computation, I need these to be dynamic. So instead of constants, I'm going to put them in registers that I can actually update during operation. So my generalized function can just do ax squared plus bx plus c, okay, where maybe these are all 8-bit numbers. A, B, and C are now in registers. So it costs me a little bit of area for the registers. The bigger cost is losing these optimizations. But it's not catastrophic, okay? So it depends how the multipliers were implemented. It might not save you very much to do this. It might save you a factor of 2 or so in your area, depending on whether they're being implemented in DSP blocks or in the logic fabric. This is pretty expensive, okay? So I had to build both operators, and then I had to build a mux. So this is at least twice as expensive in terms of area. If this is a wide data path, the mux itself is also expensive. So if these are doing not too much work, then this mux might be in the same order of area consumption as these things. So this is pretty expensive. So you can do this, you do this, but it is expensive in FPGAs. So you try to make your operators as specific as you can. Can you think of another method? Okay, so there's one way to do it. Let's say that these things change fairly rarely. Okay, I told you the FPGAs are used in communications a lot. So communication, and so one example would be your communication protocol is changing. Probably none of you remember a modem, right? Well, basically when you're negotiating a communication protocol between your house and the local node for your cable broadband, for example, there's often a training period where it's basically working out the characteristics of the line between you, and it's choosing what communication protocol to use and how fast to go, okay? And then you're going to use that for a long time. You're going to send that data for quite a while. Now, if we have no ability to do better, we're just going to build both of these things, right? We build protocol A, protocol B. Maybe there's some commonality that we can factor out into common sub-blocks. That's a bit better. But we basically build both these things. And then you can switch between them, even like per cycle. But we know you're not going to switch between them per cycle. You're going to switch between them every time you boot up your modem, which might be once every 20 days. So that's like forever in terms of clock cycles. So for those kind of cases, can you think of a better way to do this? I'll give you another example. Okay, so the big boxes, like big high-end long-distance core routers that telephone companies buy, so like Bell and Rogers, when your internet traffic makes it to one of their big backhaul networks, they basically will mux lots of data streams together and then put them on optical fibers to go a long way, right? Like to go to Chicago and New York and so on onto the next hop. So those core routers are very expensive, right? They're bringing in a huge amount of traffic, aggregating it up, converting it to optical and sending it out. And the data that they bring in is in all sorts of different protocols. They have different customers that have bought bandwidth, basically, on some of those core routers. And every once in a while, one of those customers, decides they'll take less bandwidth or more bandwidth or switch to somebody else. So Rogers or Bell would like to reconfigure that core router to take in data in perhaps a different format from somebody else and upconvert it, mux it together, and send it out over optical fiber. And there are a bunch of different rates and protocols at which people could send data into those things. But they can't take the core router down. Okay? Like if they actually just say, let's power it off, let's put a new bit stream in the FPGA with the new characteristics of the customers that are using it, they lose all the internet traffic and phone calls that are ongoing at that point, and that annoys everybody. So you're not allowed to just shut it down and say, let's reconfigure it. So what they would instead do is they'd actually build in a bunch of different protocols, and they know they'll never use them all at once, but it allows them to switch slowly these protocols between customers and use cases and never have downtime. But so for both these cases, can you think of a different way you could attack this? Okay, where your requirements are changing slowly. What do you think? Yeah. Yes, so what you could do, I mean, FPGA is reconfigurable. So unlike a processor, we can't really change what it does every clock cycle because its configuration isn't like a 32-bit or 64-bit instruction. It's like 100 million bits, okay? So we can't change that every clock cycle. But we can change it in about 100 milliseconds times what fraction of the chip you want to reconfigure. And for the use cases I've been telling you about, where it's, you're changing your communication protocol for a long time, that's a long time, right? Like that's not much time. You don't care about that. So the other method, let me see if I can find an empty whiteboard here. Ah, good. Not good. Okay, so method 2 is to reconfigure part of the FPGA. Okay, so I've got this communication system, say, that's doing some signal processing, and on a relatively slow time scale, seconds or more, I want to switch part of it. So maybe I want to go to this new F1 primed and a different G. Maybe that's G1. And here's F2. Okay, so to make this happen without taking down the rest of the system, right? So I mean, if I could just take the whole system down, then I could just say, fine, make another design and just reload that into the FPGA. But taking the whole system down is a big deal in a lot of communications applications, for example. So what I'd like to do is leave the whole rest of the design that I haven't shown here intact and running. And I just want to take this F1 and replace it with F1 prime. This G1, replace it with G2 prime, or G2. There'll be a little bit of downtime, but that's only going to affect this part of the circuit, which I'm okay with, and then it'll work again. So it is more efficient, right? I don't have to build like all of these operators. I can swap them in over time. So this is used some, but probably less than you would think. So it's a difficult design flow. It's probably getting as the tools get better and some things are added to the devices, this design flow is maybe getting a bit less difficult. And it's actually an interesting research topic. How could you make it a lot less difficult still? But I would say today it's still a difficult design flow. How many people are using or planning to use partial reconfiguration? This is called partial reconfiguration, right? Where you keep part of the design running and replace another part. How many people are planning to use this in their graduate work? Okay, so a couple. So yeah, because I'm warning you, the design flow can be difficult. But it builds character. And maybe you can take on the challenge of making the design flow better. So, okay, why do you think this design flow is difficult? So I'll write this down for posterity. So I'm asserting it's a difficult design flow. I'm going to give you some evidence for that. I mean, processors do this all the time, right? Processors do this every single cycle. You change the instruction, they're basically reconfiguring what they're doing. But in FPGAs, I'm saying this is hard. So why is it hard? Sorry, go ahead. So you're saying crosstalk? Like, nah, that's not crosstalk. Crosstalk, so does everybody know what crosstalk is? So, okay, so most people are nodding their heads. I mean, on chip, it's generally capacitive. So it's wires that are adjacent, communicating, well, affecting each other by mutual capacitance, okay? So you change this wire from a 0 to a 1, and the wire next to it basically sees some positive voltage appear, right? Or some positive charge appear through capacitive coupling. FPGAs, basically, you design it out. This is one of the things that you're getting when you buy an FPGA instead of making your own ASIC. The design team that made the FPGA has guaranteed that no matter how you use it, crosstalk will not be an issue, okay? It will not cause any glitches, which is where one wire transitions and the other one gets a pulse on it that can actually propagate through your design and break it. It can affect your timing, but that's modeled by all the tools. Does that make sense? Occasionally, I actually have had occasionally the FPGA vendors screw it up, at which point it becomes the CAD team's problem. So there's some code that I wrote in Cordis, which is actually there to solve crosstalk problems, which basically says if you use this wire and use this wire and use this wire, for God's sake, don't use that wire. None of those were like design features in the chip. Those are obviously all discovered after the fact, and you get this bizarre specification to try and go put in the CAD tools. But generally, it's just taken out of the architecture, if not CAD tools. So yeah, good thought, but no, it's not due to crosstalk. So what else do you think happens?
It's not able to change two parts at the same time. You can only change one part at a time.
So you're saying maybe I can change this, but I can't change this at the same time?
Yes, because you only have one reconfiguration port.
Yeah, so the reconfiguration time is one of it, I guess. That limits, so reconfiguration is relatively slow. It's approximately, to first order, it's about 100 microseconds, or sorry. So let's write that down. So I'm going to basically say one reason is reconfig slow. Okay, so what that means, you can write different parts of the chip. So you could write this, then you could write that. Depending on how they're lined up, they might even be written at the same time. But fundamentally, it takes around 100 milliseconds times fraction of the chip. This isn't a perfect number, right? Depending on the chip, it could be a bit more than this, could be a bit less, but it gives you an idea. So that limits, you need to be in an application that can tolerate that. So the applications I told you about can tolerate that. And you need to have logic that basically says, essentially my data is invalid for that long, right? And the overall system has to be okay with that. So it kind of limits your applicability. Okay, so that's one idea, that's one issue. What about, just think of it from the point of view of the CAD tools. I guess it's both a problem for the CAD tools, where you've given them some challenges, and challenges that you give them usually turn into challenges for you, right? So if they don't get a good result, that's your problem too. So here's the second issue. Okay, so you're thinking logically, I got to put F1 in, or maybe F1 prime. This whole design's been placed and routed. Okay, it's spread out over the whole chip, or a piece of the chip at least. F1 is in F1 is in a specific location communicating with specific wires to G. So putting in a new logic function is not enough just to write the HDL and say put this function in place of, or put this function in place of that function. It has to fit, right? Like you'd have to pick a physical region where you put F1, floor plan it. You can do that. The FPGA CAD tools will let you do it, but you have to choose a size, and that size has to fit everything that you might ever want to put there. So you usually have to round the size up a little bit, and you have to think it through. You can't basically say, I might want to stick all sorts of stuff in, I'm not sure what it is. You've got to work out how big it is. So it has to fit in the physical space. Okay, and fit means you have enough logic, you have enough RAM blocks, you have enough DSP block, you've got enough of everything. So if one of these needed lots of DSP and the other one needed lots of logic, you've got to make the region big enough for both those things, which can hurt your efficiency some. It also makes you fundamentally think a little more about the physical design, right? Like a lot of FPGA designers, they want to write HDL or high-level synthesis code, not really think too much about like how is this implemented. You're getting pulled down into a bit of a lower level where you have to actually look at where is this going. Yeah, Alex.
So is it a possible difficulty would be if I were to take a certain number of reps, just change F1, G needs to be somehow aware that it needs to ignore that signal from F1 for a little while.
Yeah, that's true. Okay, so another problem is, and again, it's solvable, but you need to be aware of it. So basically, the F1 prime outputs and F1, like all those F outputs, because they're the inputs to G, they must go to some reasonable value. While you're reconfiguring. So what I mean by that is, like, for example, they might go invalid, right? If you have a dated valid signal on this and you mark them as all invalid while the reconfiguration is occurring, that would be a good choice. G basically sees all invalid data. It stops processing. It doesn't produce any garbage. When this is done, it starts F1 prime starts producing data, marks it valid, it works again. So it's solvable, but when you write the design, you basically have to be thinking not just about function F1, function F1 prime, you also have to think some about the transition between them, right? As it's being reconfigured, it has to go to a reasonable state. Particularly, like, it can't corrupt anything. If you've got a bunch of state in on-chip RAM and you start writing all over it while your reconfiguration is happening without thinking about it, well then once your reconfiguration is done, your state is bad. If you wrote out to main memory or to Ethernet, it's even worse. So you need to make sure essentially that these modules stop processing, and you have to write some logic to do that. Okay, and I thought of one other one, okay, which is also related to the physical implementation. Yeah.
Could it also be like, so F1 prime could have different inputs?
Yeah. So the interfaces actually have to be compatible. You basically have, or you have to make a superset, right? So you need to make the interfaces line up, and you need to make them line up not just at the logical level, but at the physical level too. So I'm going to plunk in a new thing for F1. It's talking to G2 over certain wires. So, or let's just forget G2, let's just say G. So I just changed F. Whatever wires I used to talk, I sent my inputs in on, and whatever wires I sent my outputs on, I need to connect to those again. That is actually a more challenging problem for the CAD tools. Usually they're just told, get this output to this input. Now they're told, get this output to some intermediate wire. You'll see this when we actually go through FPGA routing architecture. That actually removes some of the switching. Like, you don't have as many options of switching along the way. It actually makes the routing problem that connects all the wires together harder. So let's see. Okay, so basically interface signals have to be logically compatible, but also the physical wires must also be lined up by the CAD tool. Yeah, so that makes it more difficult. As the tools get better, it gets somewhat easier. Okay, so the FPGA CAD tools are getting better at isolating the designer from some of this, but they're still not at the level where they can isolate you from everything. There are also some changes in the FPGA architecture. So this interface signals lining up, is a pain. F1 can only talk to G if that's what you put in your design, and it has to talk to it over the exact same physical wires. Some of the latest FPGAs, and we'll talk about this later in the course, have embedded hard networks on chip, which are basically have more switching. So there's another way to get data around the chip, and that method actually removes a lot of this restriction, right? If you didn't use the programmable routing, you instead use the network on chip, then your data, after you reconfigure, can get anywhere. So this problem is not, I'm not saying give up hope, right? It is gradually getting better, but it just still remains a difficult design flow, so it's not the first thing that people go to. Okay, so I'm going to talk about, so that's kind of as far as we're going in terms of streaming data flow architectures. That's kind of the most general one. But let's talk again about optimization. Okay, so we've talked about pipelining a bunch, but that's like your first thing you should do, right? If you're not meeting performance, think about whether you can pipeline. And I'm going to talk about another optimization that is kind of a nice add-on to pipelining. So let's say I've made this design. Okay, so we've got two registers feeding a lookup table, feeding a register, and then that goes to a chain of lookup tables. And then a register. Okay, and maybe I do that. There's some fan out here. Okay, so I do have some pipelining because I've got this register in the middle. So let's say I started off with, I put this register in there. When I look at the delays, so the timing analyzer in my CAD tool says that's 2 nanoseconds, that's 6 nanoseconds. So my clock period is going to be limited by the longest path. I can't clock it faster than 6 nanoseconds or about 166 megahertz. So this probably wasn't the best pipelining, right? I could have chosen a cut line here. And it would have given me a more balanced critical path delay. So, a designer can go back, move the registers around, try to do a better job of balancing this. But this can also be done automatically. So this is an optimization called retiming. So, and retiming can be done by hand. Like if you know the algorithm, you can apply it by hand in a mechanical way, but also CAD tools can and do it automatically if you allow it. Okay, so what retiming is it basically it doesn't change, pipelining changes the latency of your design, okay? So CAD tools won't automatically pipeline because it is still visible from the outside of a module. Right? It does the same function, but with different latency. They can't say if that's okay or not. That's why a designer generally has to go in and do the pipelining. Retiming, CAD tools can do automatically as long as you enable it, and it is normally enabled by default nowadays. So, and the reason is you can't even see a latency change when you retime. It just moves around existing registers. So, okay, so what it does is it moves registers forward or backward. Across logic to balance delays. Balance basically timing paths. Okay, so for that, relatively poorly pipeline design up there, what retiming would do is it basically looks at the timing paths on each side of each register. And I've only put one interesting register in here. So we'd look at this one and it would say, on this side, you're actually limiting the speed of the circuit. You're on the critical path. And on this side, you're not. If the critical path is 6 nanoseconds, you have 4 nanoseconds of what's called slack. You could slow down by 4 nanoseconds and still not impact the circuit. So it will see that it is beneficial if it can move this register forward across logic to try to get less delay on this timing path at the expense of more delay on that timing path. And it can do that in a mechanical way. Basically, it says, okay, if I don't want this register here, I have to move it to its outputs. Okay? So in this case, moving this register to this logic that is downstream of it, so forward retiming, is going to involve making 2 copies of it because it has 2 fan-outs. Does that make sense? And the CAD tool can do this automatically, and it will not change the latency of any input to output path, meaning it doesn't break your circuit. Also, it doesn't actually even, and it doesn't change the latency. So it won't break your functionality, and you can't even tell that the latency has changed. It's invisible to the outside world, which is why CAD tools can and do this automatically. So after you turn on the retimer in your CAD tool, it basically would restructure the circuit so it looks like this. You've got this L1. That branched out to these 2 functions, L2, whoops, and L3. And I moved the register after those. And it actually turned into 2 copies, okay, because I had to move it to both fan-outs. You can think of it as retiming as like automatically choosing a different cut for a register, but it's kind of a local operation. Okay, L4, L5, L6, and L7. So the rest of the circuit's unchanged. Okay, so can be automatic. So FPGA CAD tools used to turn this off by default, and now they generally turn it on by default because it's become so important as FPGA designs have become more deeply pipelined, and pipelining has become more and more important to their performance. Well, there's just a significant benefit to just leaving this on. So if you put the registers not super well balanced, the CAD tool will try to rebalance them. It's still best to try to put them in roughly the right spot because you're making the CAD tool's job harder if you just put registers all over the place. Like if you put all your registers, a whole bunch of registers here, like just a sequence of registers and then a sequence of combinational logic, the CAD tool will try to move the registers around across that logic to speed things up, and it'll do a reasonable job of it. But it's still hindered by the fact that you put them in not a very good spot, because sometimes it has to run some early parts of the CAD flow to figure out these are not in a good spot, and then it tries to move them. It's better to give it a hint if you know this is a better way to write the HDL. But you don't really have to fine-tune it perfectly. And the CAD tool actually, in the later stages of the design implementation, it goes through many stages, right? We do synthesis where we make the basic logic, then we go through placement where we choose where to put it, and then routing where we hook things together. Xilinx or AMD and Intel's CAD tools at least will do retiming multiple times, including when they have more information about the exact delays, because they actually are starting to know exactly where they're putting things. So they can do fine tuning that's actually hard for you to do, but they still benefit from you getting the registers in roughly the right spot. You can turn this off. Okay, as I said, it used to be off by default, now it's on by default. Why do you think you might turn this off by default? Why might you turn this off? Yeah. Yeah, it does. It can shorten your compile time. There's another reason that people would turn this off. It can increase resources. It usually doesn't by too much. The case I showed you does do it. Does increase resources. I mean, you can actually have cases where you have registers here, and it's better to move them backwards where it actually shrinks. So it can go the other way. Another reason is basically simulation. If somebody's actually debugging a design, and so they're running it some in hardware, reading out registers, looking at those, simulating it to see what's going on, retiming